Okay, so this is going to be an example where we've got a bunch of atoms at t is equal to 0 seconds. We've got 1.0 times 10 to the 6 atoms, and they have been excited to an upper energy level. So they're in an excited state. We've got these electrons in this upper energy level, and over time they're going to decay back down to the ground state. And when they do that, they're going to release photons. And so we're told that at some later time, 20 nanoseconds later, 90% of these atoms, their electrons, have jumped back down to the ground state. So first question, how many photons were emitted? Okay, well, first of all, we've got 90% of the atoms have gone back down to the ground state, so 0.90 times n, our number of atoms here. So that's 0.90 times 1.0 times 10 to the 6 atoms. That tells us that 9.0 times 10 to the 5 atoms have jumped back down, to the ground state. Now each one of these atoms that have jumped back down to the ground state have released a photon, so this implies that there's been an equal number of photons released. So 9.0 times 10 to the 5 photons were emitted. In that time frame. So in that 20 nanoseconds. Okay. So it all happens pretty quick. We release the photons, 90% are back in the ground state. Now, given this information, what is the lifetime of that excited state? Now, clearly, lifetime is pretty short. And the lifetime, remember, is this tau value. Gives us the time scale of this decay process. Okay, so to think about this, we're going to say, well, at t is equal to 20 nanoseconds, 10% of the atoms are still in the excited state. 10% of the atoms are still in excited state. 90% are back down to the ground state, so 10% are left in the excited state, and that's 10 to the 5 atoms, right? That's 10% of 10 to the 6 atoms. So this 10 to the 5 atoms are remaining. So we'll set up our equation for these decay processes where we've got the number that are still in that excited state is equal to, well, how many did we start with and not? And we've got this exponential decay term here where we've got the time elapsed and we've got the tau value, the lifetime, giving us the time scale of this process. And that's what we're interested in, this tau term. Okay. So the number that are still left at this particular time is 0.1, so 10% of the original number, and naught is equal to n naught e. Now in this case, at this time, t is equal to 20 nanoseconds. So this is e to the negative 20 nanoseconds over our tau value, our lifetime value. Okay, now we want to get this term, so I'm going to take the ln of both sides, and these two are going to cancel, right? So these two cancel. So I end up with ln 0.10 on this side is equal to ln e to negative 20 nanoseconds over tau. Okay, and this term will come down. So we end up with negative 20 nanoseconds over tau equal to ln 0.10, and that's just a number. I'll keep it as ln for this line. Looks a bit more neat and tidy. So now we isolate tau, and tau is going to be negative 20 nanoseconds over this. Well, ln of 0.1 is negative 2.3. That makes sense that the negatives now cancel because we want a positive time here. Expect a positive time. And so we get a tau value of 8.7 nanoseconds. So there's our lifetime. Now, does it make sense? Because this is a smaller amount of time than this is. But yes, this makes sense because, remember, recall that, when t is equal to tau, we have our remaining number is a factor of 1 over e times n naught, right? Because our t is going to be tau, so this will be negative 1. So this will just be n is equal to 1 over e n naught, and that's equal to, this is like 37% of n naught, right? So it's going to take a shorter amount of time to get to 37% of the original value. It's going to take a little bit longer amount of time to drop back down to 10%. So all of this kind of makes sense, okay?